So a few days ago, this would have been, I think, Wednesday or Thursday of last week, we looked at conservation of mechanical energy. We defined mechanical energy as being the sum of potential and kinetic energy. And we said that it's conserved if the sum of potential and kinetic energy is the same for the object's journey anywhere in the journey. So if it's a pendulum swinging back and forth, and I could measure the potential and kinetic energies and add them together when the pendulum is at one place, and then I measure the potential and kinetic energy of the pendulum at a different place, if the sum is the same, then that means that kinetic energy and potential energy was conserved. Okay. And since kinetic and potential energy added together are mechanical energy, we would say that the mechanical energy is conserved. That only happens if no work is done and no forces of friction are present. So I think it's also important, as well as you being able to solve problems with numbers, that you understand why this is the case. Work is a transfer of energy. So if no work is done to the system, then no energy is added or taken away from the system. Friction is a force that produces heat energy. So if there is no friction, then there is no energy lost to heat, which means the mechanical energy is conserved. Well, what if work is done? Well, if work is done and I've got up here, I notice I've got to increase the energy of the system. Really, you know what that should be, is to change the energy of the system. And the reason is, although work is a scalar, it's not a vector, it doesn't have direction. Although work is a scalar, work can be negative. Work can be positive, in which case you're adding energy to the system, or work can be negative, which means you're taking energy out of the system. But if work is done, then you use what's called the work energy theorem, which says that work done is the change in energy, and change in energy is final minus initial energy. If you take the final energy and subtract the initial energy and get 0, then that means that the final and initial energies were equal, which means no work was done, which means it's conservation of energy. The other possibility is heat is produced by frictional forces, in which case you use the idea that heat is an amount of energy or work produced by a force of friction. Your formula for work is work equals force times distance. So heat is force of friction times distance. And heat is always the final form of energy. If you had heat being produced because there was a force of friction, then you would always include the heat at the end. All right. Questions? This was assignment number 1 this time. Any questions? Aoki. Number 5. Okay, let's take a look at number 5. So you have an 18 Newton box. I'm just going to stop us right there. The fact that you're told it's an 18 Newton box means you know the mass as well. I mean, we have to calculate it. We don't know it yet, but if I want to find the mass, I can take that 18 newtons and divide by 9.81 newtons per kilogram. If I need the mass, I have it. I'm not even going to calculate that. Slides from rest down that incline as shown. The box reaches the bottom with a particular speed. What's the force of friction along the incline? So there's friction, which means that I cannot say E mechanical at the top equals E mechanical at the bottom. I'm not allowed to say that. That is just not true because there's heat. I can say, however, E at the top equals E at the bottom. And as long as I don't say mechanical, I'm allowed to work with this. Because heat is a type of energy. It's just not mechanical. What kind of energy does this object have at the top of the incline? Well, it's above the lowest point, so it has gravitational potential energy. But it's not moving, so there's no kinetic energy. And there's no heat yet, because at that initial point, the force of friction hasn't been acting on it. No heat is being produced at an instant in time. At the end, it will have kinetic energy. And because that bottom of the ramp is the lowest point, we're going to end up saying that this is H equals 0, and that's why I don't put mgh here on the other side of this equation. There is no mgh at the bottom, but there is heat. And I'm choosing to show this to you this way rather than writing in a formula for heat. I'm just going to leave it as heat. In order to find, well, I'll ask you a different question first, I suppose. Can I cancel the masses? No, I cannot. There's no mass in the third term to be canceled. I can't calculate mgh yet because I need to know what h is equal to. That's a trigonometry problem. The height is opposite the 30 degrees. The 0.85 meters is the hypotenuse, so I can write sine of 30 degrees equals the height. That h stands for height, not hypotenuse, over 0.85 meters. I believe what you're going to get is 0.425 meters. Okay. So we have the mass. I guess I need to know the mass, don't I? So I'll go ahead and follow through with that calculation. 18 divided by 9.81 give me 1.83. I'm going to carry all those decimals. In fact, I'm going to store that as m for mass. But I'm just going to write 1.83. So I have 1.8. I'll just write 1.8 times 9.81 newtons per kilogram. That's interesting. I guess, you know, for here, I didn't even need to calculate m. I could have just put for mg 18. I can't do that here, though. 1/2, the mass was the 1.8 whatever, times the speed at the bottom is 1.6 meters per second, quantity squared plus the heat. And what I would like everybody to do, please, is I want you to calculate what this term is and what this term is. So I'm not asking you to solve for anything yet. I just want us to calculate each of these two things. Because I just want to point out the discrepancy here between the mechanical energy at the top and the mechanical energy at the bottom. The mechanical energy at the top is almost 8 joules. Well, 7.65 joules. But when the box gets to the bottom, when the box finally makes it to the bottom, how much mechanical energy does the box have? Well, 2.349 joules. So where did that mechanical energy go? It must have gone into heat. Which explains why mathematically you can see that you have to take the 7.65 minus the 2.349. And that's going to be the heat. So I'm doing this in stages for a different reason as well. I'll show you in a second. So if I subtract 7.65 minus that kinetic energy at the bottom, I get the heat equals 5.3 joules. And we're not asked to find the heat, we're asked to find the force of friction. Heat equals force of friction times displacement. Now, I was almost going to do this up top here. But I didn't. And the reason is, as soon as I do that, students will get in the habit of doing it all the time. But if I gave you a question that just said, find the heat, you're not going to do that. You're going too far in your algebra or your formula. So I decided to leave the word heat in there just in case you're asked, what's the heat produced? Now that we do know what the heat is, you can take that 5.3 joules and set it equal to the force of friction times the displacement. I'll do this in stages. The displacement is the actual length of the surface that the box was scratching on, that the force of friction was existing between. So it's the hypotenuse of the ramp, not the height. And it looks like maybe that solved any problem you might have had with this. So we have to take the 5.3 joules, set it equal to the force of friction, multiply by the 0.8, was it 0.85? Okay. So if we divide that energy that's heat by 0.85, we get a force of friction of about 6.2 newtons. Is that okay? Okay. Any other questions before we get started today? Yeah? Okay, let's look at number 2. A 75 kilogram box at rest slides from the top and it reaches a speed at the bottom, and we're asked to find the force of friction. This is really, I think, the same idea as the one we just did, I think. Since friction is there, what we can do is say EI equals EF. It's just that we don't want to say that's mechanical. By the way, the only time you introduce work is if work is done. EI here would be mgh at the top. That's all the energy that's in the system to begin with. EF is 1/2 mv squared at the bottom plus the heat. Now that I've had the discussion that I had with Aoki's problem, there's nothing wrong with you putting force of friction times displacement here because you are after the force of friction. I'm going to leave the word heat though. I want you to get into that habit. The thing that makes this just a little bit different is that we don't have to calculate the mass. The mass is given to us. So I can put 75 kilograms times 9.81. The other thing with this problem is you're actually given the height of the ramp, so we also don't have to do a calculation there. This is equal to 1/2 times 75 kilograms. I'll fix that other number in a second, times the speed at the bottom squared. This should be 75, not 7.5. And then this is plus the heat. Same thing that we talked about with the previous question. If you calculate mgh, what you're finding is the total energy in the system at the top, and it happens to be 100% mechanical. When you calculate the 1/2 mv squared, what you're finding is the mechanical energy that's still in the system at the bottom, and the difference between them will be heat. So in this particular case, Nate, I'm not going to calculate them both separately. I'm going to take mgh minus 1/2 mv squared. 75 times 9.81 times times 6 minus, that's the energy at the top, 0.5 times 75 times 5.2 squared. I'm going to ask a weird question here. What would happen if I hit equals and I got a negative? I mean, I don't. This is the heat produced. But what if I got a negative? That's a really good answer to that question. You probably entered it wrong, or there's a flaw in the question. You can't get a negative here because then you would be saying the box has more mechanical energy at the bottom than it had at the top, which would mean energy was added to the system because you also have heat. Could you have a situation where you have more mechanical energy at the bottom? Yes, if work was done. If somebody was running along behind the box as it was sliding down, applying a force. But we don't have that situation. So this is just, before I hit equals, I just thought, well, I want to point out to you, you can't get a negative. That, Nate, is the heat produced, 3,400.5 joules. That's the heat, but heat is the force of friction times the displacement. So if we take 3,400.5 joules and divide by the displacement of 12 meters, we're going to get the answer. So about 283 newtons. And I think they have 2.8. We have 2.8 times 10 to the 2. All right, we are going to move on and look today at the final topic in this unit, which is power. And tomorrow, Thursday, and Friday, we're going to be doing a number of review activities. This lesson is on page 46 of your unit handout. So power is something that we have to define, and then we're going to be solving problems involving power. And we start off, we dive right in, and we look at the definition of power. Power is the rate at which work is done. So if you just not even look at those formulas just for a second. Power is the rate at which work is done, or the rate at which energy is used. Until you get to maybe a calculus class in university, or even high school rather, rate means something very specific. It means measured relative to time. So if I say, you know, I want to talk about the rate at which I spend money, it would be so many dollars per day. If I want to talk about the rate at which I eat chicken wings, it would be so many chicken wings per hour. If I want to talk about the rate at which I mark exams, it's so many exams per hour. The rate at which an object moves is so many meters per second. The rate at which velocity changes is meters per second. So the rate at which work is done, or the rate at which energy is used, can be found using either of these formulas. Power equals work over time, or power equals change in energy over time. But I hope it's not a big surprise that these two formulas are the same, because work equals change in energy. So whether I say power is work over time, or I say power is change in energy over time, is really not important. However, if you look at your formula sheet, they only have this. And it's a bit of a pet peeve of mine. I wish they only had change in energy over time, and you'll see why in a minute. Anyway, there's your power formula. It's under the momentum and energy section of your formula sheet. By the way, that very first formula and the second formula below it, these two are formulas we do not learn about in Physics 20. We're going to be using them in the first unit of Physics 30. So there's your formula for power. Power equals work over time. If you take a look at the units of power, well, if I take work divided by time to get power, work is measured in joules and time is measured in seconds. So work over time would be measured in joules per second. However, we abbreviate a joule per second. Remember when we talk about force, which one formula for force is F net equals ma. Remember my story of telling you that Well, that means that this is going to be so many kilograms times so many meters per second squared, which means a force has units of kilograms times meters per second squared. But remember me telling you, well, let's just abbreviate that. We call it a Newton. You know, on the other hand, so we have a Newton is equal to 1 kilogram times a meter per second squared. A joule is equal to a kilogram times a meter squared per second squared. There's lots of ways to demonstrate that. One of them is to look at this formula for kinetic energy. If I take the units of mass, it's kilograms. The units of speed are meters per second. But I'm squaring the units of speed. I get meters squared per second squared. Okay. So we do the same kind of thing here. What are the units of a joule per second called? Does anybody know? Declan? It's a watt. It's called a watt. Named after, I want to say Charles Watt. I don't know though. Here's why I don't like the formula on your formula sheet. This is abbreviated W. But the formula is this. And it has a capital W in it. The units of power are a watt. The units of work are joules. The units of time are seconds. So we have W appearing twice, and I think it causes confusion with students. And what I'm going to end up telling you is, although you will see problems where you're told so many watts, I want you to try to remember that a watt is a joule per second. And then really, and we'll look at examples of this throughout the way, a lot of the time you don't even really need a formula. You just go, well, it's so many joules per second. Let's use a ratio to answer the question. Sometimes you do need the formula. All right, so a question. Compare a 60-watt bulb and a 100-watt bulb in terms of the energy used. These are 60-watt LED bulbs or 60-watt incandescent bulbs. What it means is that the 60 watts is referring to the total energy. I'm going to go back on that and change my mind. These are incandescent bulbs. An incandescent bulb is a bulb that you probably can't buy in a store anymore. It's got a wire in it, so it has a tungsten filament made out of metal tungsten. One end of this filament is connected to a metal screw piece. The other end goes through here and is connected to another piece of metal. And when you connect a battery that has a positive terminal and a negative terminal, or a power supply, and you connect, say, the negative to here and the positive to there, it causes electrons to flow through that wire. And we talk about this extensively in Physics 30, but when the electrons move through the wire, they lose their electrical energy, and that electrical energy is turned to heat and light. And if you've ever touched an incandescent bulb before, one that has a filament, it's quite hot. And most of the energy in these bulbs is heat. It's about 95% heat and only about 5% light. So what does this mean? If we have a 60-watt bulb, that's 60 joules per second compared to a 100-watt bulb, which is 100 joules per second. There's your comparison. The 60-watt bulb uses 60 joules of energy per second. So each second, $60 joules of heat and light are produced. And what that means is each second that the bulb is operating, you're using 60 joules of energy, which means you're paying for 60 joules of energy every second. When you look at an electrical energy bill, the energy is billed as so much per gigajoule usually, but it adds up. If you leave the lights on in the house, that you're paying for that. Someplace in your house, it could be in your basement or it could be outside, there's a meter. It's an electrical meter. And if you look very closely at the meter, even if it's digital, it should have a metal disc that spins around. And when you look at it first, you can't really see it spinning, and then you'll see a black line go by. Just as an experiment, go home, turn on everything in your house, turn on all your bulbs, and go outside and watch that spin around. It goes quite fast. If you turn off all of that stuff, it goes slower. 100 joule per second, or a 100-watt bulb, obviously, is 100 joules every second of heat and light that are being produced. I misspoke earlier when I said this could be an LED bulb. If you had a 60-watt LED bulb, it would be blindingly bright, right? Because if I'm telling you that only about 5% of the energy in these bulbs is light energy, if all of it were light energy, which an LED bulb heats up a little bit, but not much. If all of it were light energy and it was a 60-watt LED bulb, it would be about 20 times as bright, which, you know, you wouldn't need that. Which is why when you buy an LED bulb, you'll often see on the packaging something like 2.8 watts, equivalent of 60 watts. It will tell you something like that. Okay. All right, what are the units of power in standard units? Okay, so power is a watt, which is a joule per second. A joule, I'm going to use mgh this time to show you what a joule is. I just used 1/2 mv squared right here. But if I use mgh, the unit of mass is a kilogram. The units of G, I'm going to dive right to meters per second squared and avoid the newtons per kilogram. And the units of height are meters, which means the unit of a joule is a kilogram meter squared per second squared. And look at it. Meter times meter is meter squared. That's the same as the set of units I got when I used 1/2 mv squared to find a joule. So we have kilograms, a watt. This is a watt, right? A watt is a kilogram meter squared per second squared per second. Now, some people have a difficult time with fractions like this, so I'm going to teach you what I would tell you in a math class. This is a fraction that has a troublemaker in it. That second squared is a denominator of a numerator. We don't want mini denominators. So the best, most efficient way to get rid of that second squared is to multiply the top and the bottom of this fraction by second squared. And what you end up seeing is that the second squared cancel here, and you're left with a watt is equal to a kilogram times a meter squared over a second cubed. Now, don't try to wrap your head around what that means. It just happens to be the combination of units that will give us the unit of power. And the only reason why I'm doing this with you is because in Physics 30 we do that a little bit more. I don't want you to take Physics 30 and just be blown out of the water by talking about standard units. It's something that I hope you've seen before. All right, let's get to the examples now. Oh, one more thing, right, efficiency. Efficiency typically refers to a percentage of useful work. So, for example, if I had a motor, and that motor is used to lift a pallet of shingles, to a height, what type of energy do I consider useful here? Potential energy, right? So if the potential energy up here of these shingles is 1.5 times 10 to the 6 joules, that energy had to come from somewhere. Well, this motor is attached to some power supply. I'm going to not use the word power supply. I don't want to talk about power just yet. Some energy supply. Maybe it's a generator, maybe it's plugged into an outlet, maybe it's running off of a vehicle's power supply. I don't know. But if we have a total of 2.0 times 10 to the 6 joules used, then not all of the energy used was actually used for a useful purpose. Right? Less energy was actually useful. By the way, where did the extra energy go? Alex?
Heat.
Probably heat. Also some sound energy, which we haven't really talked about. A little bit of kinetic energy because the things were moving, but not a big amount. So if I said to you, what is the percent efficiency? You would take that 1.5 times 10 to the 6 joules. You would divide by 2.0 times 10 to the 6 joules and multiply by 100. And in this little made-up example, if you could do that calculation for me and confirm, you get 75%. 15 is 75% of 20. It's my thinking anyway. So you get 75% efficiency. I'm just throwing this off-the-cuff example out to explain to you what efficiency means. If the motor is 75% efficient in doing its job, then only 75% of the output of the motor is useful. The input, which is 2 times 10 to the 6, is the total, but the useful energy is what it's used for. So when I talk about those incandescent bulbs, the efficiency there is about 5%. Because you use those bulbs to produce light, right? All right, let's take a look at some examples now. An elevator and its occupants have a mass of 1,300 kilograms. The elevator motor lifts the elevator to the 12th floor, a distance of 30 meters in 75 seconds. What type of energy transfer is made to the elevator and its occupants? Gravitational potential. We've had this little discussion numerous times. Does the elevator move? Yes. So is there kinetic energy involved? Yes. But you're not accelerating the elevator the whole time. You're just getting it moving very slowly, and then you're going to lift it at that constant speed. What is the power output of the elevator? Well, power is joules per second, which means it's going to be the potential energy of the elevator and its occupants over the time. I want you to notice I've very kind of cleverly not written down the formula for power. I didn't write power equals work over time. I really don't like that. If you want to write that, you can. But if I was forced to write a formula here, I would have written instead power equals change in energy over time. I just don't like that P equals W over T, because W is work, but it could be confused for watts. Or just put the numbers in. The mass is 1,300 kilograms times 9.81 newtons per kilogram times 75 meters, nope, times 40 meters over 75 seconds. And this is going to be the answer in joules per second or watts. $6,801, $6,802, okay. And in fact, when I write the units of power, I will almost always write watts. There's nothing wrong with this. There's nothing wrong with writing 6802 watts that way. But W is the letter we use for work, and I think it can be confusing. What this means, by the way, is 6,802 joules per second. Now notice the question said, what is the power output? That's what comes out. Take a look at the next question. If the efficiency of the system, what is the efficiency of the system if the motor generates 9.4 kilowatts of power to do the work? Well, 9.4 kilowatts is 9.4 times 10 to the 3 watts, which is 9,400 joules per second or watts. And I want to back up and look at the efficiency formula. If efficiency is energy out over energy in times 100, could I also use power in and power out? Yes, because it's power is energy per second. So I'm going to give you a second formula here. This could as well be power out over power in times 100. And these formulas are not given to you. You need to understand it's a percentage. That's what we're dealing with. And whether you're talking joules over joules or watts over watts doesn't matter. So what is the percent efficiency? Well, the total energy available in terms of joules per second is 9,400. The useful was 6,802. I mean, you should be able to just look at those and see that that's around 68, 70%. More than 70%. But do you get the idea? You're finding a percentage here. We just multiply by 100. The units cancel, so percent efficiency has no units. So divided by 9,400, multiplied by 100, gives 72% efficiency. Any questions with that example? All right. Let's take a look at the next question. A 1,250 kilogram car accelerates from 10 to 30 meters per second in 6 seconds. What's the power output? Does it mention we're going up a hill? No. So we're not going up a hill. You know, otherwise you couldn't answer the question. We're assuming a level surface. So what kind of energy change? I'll go with a formula this time. Power equals change in energy over time. What kind of energy change does the car undergo? Zahara? It is kinetic. So this is a kinetic energy change, which is final kinetic energy minus initial kinetic energy. Remember, change in a thing is always final minus initial. And, you know, if you could go back in time, by the way, to the first week or two of classes when we learned those kinematics formulas. And if I could back then show you some of the formulas you're developing or going to be developing, you might run from the room because it's really scary. But you guys have come a long way. Those kinematics formulas were a big challenge for you back then. Now you're building these big equations. So my point is when I write 1/2 mvf squared minus 1/2 mvi squared, this should not be a big shock. It shouldn't be like, oh, look at that formula. Nothing about that is complicated. You have a change in kinetic energy divided by the time. Kinetic energy is 1/2 mv squared. By the way, you can calculate 1/2 mv squared outside of this if you like and subtract them. But I'm going to put it in here. Alex, you're going to be my guide here. It's 1,250 kilograms. 30 meters per second is the final speed.
Yeah.
Don't forget to square that. 10 meters per second is the initial speed.
Yes.
I cannot remember the time.
6 seconds.
Thank you. So when you calculate the 1/2 mv squared minus the 1/2 mv squared, that will be joules, and then divided by 6 seconds will give you joules per second. By the way, I don't know if any of you were tempted to do this. You cannot just subtract the two speeds and do one calculation with 1/2 mv squared. It will not work. .5 times 1250 times 30 squared. I mean, if I were to hit equal right now, that's the final kinetic energy. Minus the 0.5 times 1250 times 10 squared, which is the initial kinetic energy, gives me this many joules. Do you get that number for the top? Divided by 6. So about 8.3 times 10 to the 4 watts. And again, I would just prefer to write watts or joules per second. Okay, the engine is 42% efficient. Internal combustion engine vehicles, ICE vehicles, not electric or hybrids, but engines that run on gas, are really not efficient. If you've ever accidentally leaned on an engine part after it's been running, you will understand why. There's a huge amount of heat produced. The engine is only 42% efficient. What is the power of the engine in horsepower? How many of you have heard of horsepower? That literally means there was a time where, I mean, all horses are different, but whatever a horse could do in joules per second, that was called a horsepower. And 1 horsepower is equal to 746 watts. Let's just shelve that piece of information away, and let's find the power of the engine in watts to begin with. Okay? So what we know is that the percent efficiency is the power out over the power in times 100. And the percent efficiency is 42. The power out, well, the engine is used to accelerate the car. So this kinetic energy gain per second is the power out. It's the useful power. 8.3 times 10 to the 4. And I'm actually going to write in 83,333.3. I'm going to use all those decimals, or a lot of them. So 83,333.3 watts, or joules per second, over the power in times 100. And by the way, when you're trying to find a total, there are some weird things that people think they can do. They think they can maybe take 42% of that and add it to it, or 48%, or 58% rather, and add it to it, and then try to come up with some weird way. You can't. You have to solve it this way. So how am I going to get that power in? Well, let's cross multiply, and I'll get 42 times the power in, which is, when you look at the question, that's the power of the engine. It's what the engine is producing. No, only 42% goes into speeding the car up, though. Equals 83,333.3 times 100. So to solve this is pretty straightforward. You're going to take that power that we calculated times 100 divided by 42 and get an answer. So this is the power of the engine, 198413 watts or joules per second. And just to demonstrate that this is right, if this is right and the engine is only 42% efficient, then 42% of this better give me that 83,000. Okay. We still have to do a horsepower thing. 1 horsepower is 746 watts. We're simply going to use a ratio. 1 HP is 746. Did I get that right? 746 watts? Okay. Equals X horsepower over 198,413 watts. So looking at this, when I cross multiply, I'm going to have to take this number, and I'm going to have to divide it by 746. I got to take that times 1 divided by 746. And I don't know, how many of you, just without writing out a ratio, recognize that's what you would do to find out how many horsepowers? You know, if that's that much energy and there's only 746 per horsepower, you're going to divide. About 266 horsepower. Next example, a car has a particular mass. It's traveling up a hill at a constant speed. That constant speed is very important. The speed is 90 kilometers per hour, which is exactly 25 meters per second. There is a backwards force of air resistance of 450 newtons, and the slope of the hill is 6 degrees. When I draw this, I'm going to exaggerate the slope. That's more than 6 degrees. Okay. I'm also going to use, the traditional block, which represents the car. I'm not going to draw wheels or anything like that. As this car is going uphill, there is a force backwards of 450 newtons. Here's a question for you, and this is a tricky problem. This whole problem is tricky. If it's moving at a constant speed, that means the forces are balanced. So if I said to you, what's the forward force? And you said, well, it's 450 newtons. Why is it not? Is perpendicular the word you want to use? The parallel component of gravity. Gravity is also pulling the car Now, it's only 6 degrees, so it's not going to be a huge force, but there is a parallel component of gravity acting down the ramp or down the hill. What is the parallel component of gravity? It's the force due to gravity times the sine of the angle. You do not need to know that. It would be given to you on an exam. So this would be m times g times sine of 6 degrees. Well, let's calculate that. The mass is 2K, 2,000 kilograms, times 9.81 times sine of 6 degrees, making sure I am in degrees, and I am. As well as the 450 newtons downhill, there is also a backward force, in terms of the car's motion, of 2,050.85 newtons. Do you get the same number? Okay. So we also have this force, the force due to gravity parallel, which is 2,050 newtons. I can carry more decimals, but the point is we have a total force of 25 newtons downhill. That means, since it's moving at a constant speed, we have to have a total force uphill of the sum of those two forces. The first question here is not got anything to do with energy or heat or power or any of that. It's just a problem from earlier on in the course. So the answer to this question is 2,500 newtons. Are you with me? The most important part of this question is the next piece. What is the power output? Well, the power output, we want to be careful here. The power output of the engine, that means the total power used. Some of it is going to go to heat. Some of it is going to go to keeping the car moving against friction, which is where the heat comes from. Some of it will go to an increase in potential energy. But the bottom line is power equals the work done over the time. And the work done is force times displacement. And it's the applied force times the displacement over the time. Here's the problem, though. Do you know the applied force? What is it? 2,500 newtons. We just found it. Do you know how far the car travels? No. And you don't know how long the car is traveling. But we can be clever about this and say, you know what? Power, if power is force times displacement over time, then isn't power the force times the displacement over time? I mean, does it really matter how I think of that algebraically? I can take the displacement over the time and multiply by the force, or I can take the force times the displacement over the time. However, if I look at it this way, what is that? That's the speed of the vehicle. That's 25 meters per second. Whether it's 50 meters and 2 seconds or 250 meters and 10 seconds, the ratio of that is the speed. And that means I can take that 2,500 newtons and multiply by the speed of 25 meters per second. By the way, newtons times meters is force times distance, which is work, which is joules, divided by the seconds is joules per second. And I get 625 followed by 2 zeros, I think. Joules per second, or 62500 watts. And if you are fine with just writing W for watts, then feel free. I just don't like seeing it too often. If you want to write it, it's not that I'm going to look at it and correct you. I personally don't like writing it as a teacher because I think it's too easy to confuse it with work, which is a totally different idea. All right. I think it's maybe a good idea to work on the additional problems. How many do I have on the back there? 4? Get to work on those. If you get those done before the end of the class, which is in about 15 minutes, then you can try a couple from the textbook. It doesn't really matter.